Recording is rolling. It is Monday, March 11th. You guys get to start learning about theory of relativity today. That's going to be all this week. All right, so I just gave you guys the thumbnail notes version of the new posters that are there. My wall over there with the purple banners. All right, so I'm going to be using those to go through the story of relativity today. Right? Tell you guys a little about the history behind this, what led to this thought process, what some equations, what some implications. Got a short animation for you guys. You guys ever heard of something called twin paradox? Okay. We're looking at it today. Right. Before I get too far into that, I know I mentioned this last week, but it's worth mentioning again, is that on April the 8th, so about 4 weeks from now, there's going to be a total solar eclipse. And this is going to be the last, This is going to be the last one in the States for the next 20 years, So some stuff on that. A few months ago, there was a solar eclipse. It was this yellow band here. The yellow band means it wasn't a total eclipse. There was always some part of the sun visible. And we could see most of that from Florida, like over half of it. You guys remember we made these pinhole cameras, or if you want to do even better, you get some of these solar eclipse glasses. If you want some of these for this next eclipse, then probably get them about now, right? Not like the day before when it's probably hard to find them. But yeah, if you order them now, you should be able to go. Right? And the one a few weeks from now, on April the 8th, that's this right here. And it's blue on this map because that means it is, in fact, a total solar eclipse. So if you're standing anywhere underneath this blue band, you will see the moon completely eclipse the sun. Okay. So yeah, if last one for the next 20 years, if you guys want to like take a road trip to Arkansas, something like that, and catch that, it's going to be on a Monday. Might be wanting to work that out with your parents right now would be a pretty good idea. All right, so with that, let's switch over to relativity. So I've got a question for you guys. Question. Right, this is gonna come back later today. Remember when I was studying for? Did you guys do a test called the FCAT, or do they change the name of it? Yeah. Okay. What FSA, is that what they call it now? Yeah. All right. Yeah. Here in the States, like every 5 years, got to change everything. All right. So there was this question that kind of intrigued me, and it's kind of related to this theory of relativity we're going to be doing today. I should give you guys a different version of this, but suppose there's like a lake next to a river, right? They got a couple of guys with boats. So here's a boat. Here's a boat. There's this guy standing. Got these guys standing in these boats, and if they were to race side by side in the lake, they can both paddle about as fast. I'll say the paddle is, let's call it 10 meters per second, which is kind of fast, but it's a nice round number, right? So they can paddle at 10 meters per second. Okay. And then they started thinking, hey, what if one of us is in the lake and one of us actually goes to this river? Now this river, let's say the downstream current, I'll say the current, right, is like 5 meters per second. Right. Now, if they just go downstream, then the guy in the river is going to definitely beat the guy in the lake because he's getting a boost from the current. Okay. But then they're looking at this tree down at the far end of the lake and say, hey, well, let's actually do this. Let's race all the way down to the tree and then back to the starting point. So here's the start finish line right here. Right, so start finish. Okay. So the question is then, who's going to win that race? The guy in the lake with the stagnant water, or the guy in the river who's getting a boost from the current one way, but then has to fight the current the other way? Okay. And I'll give you guys sort of a hint, is that they don't tie. Somebody actually does win. Who wins, the lake guy or the river guy? Let's see a show of hands what you guys are thinking. Or maybe you've worked this out, or maybe you've seen this in math class and you know the answer. Who says the guy in the lake wins? The lake guy. Who says the guy in the river? Ooh, all right, so I'm seeing some votes on each one. Let's run some numbers. Okay, I gave you guys some speeds. Let me throw one more number on the board so we can calculate something. Let's say that this distance is 120 meters. Okay, these numbers work out pretty good. Okay, so now what? Okay, well, I know that distance equals speed times time. Okay, so that's all good. Okay. And see, it's the same distance, different speeds maybe, and whoever wins the race has the smallest time for some distance. So I'm going to rearrange this and get time is distance divided by speed. Okay. Okay, so the time for the guy in the lake is, well, he goes 120 meters across and 120 meters back. So that's 240 meters total. And he does that at 10 meters per second the entire way. So that's like 24 seconds to finish the race. So there's the guy in the lake, right? Now the guy in the river, one way he's getting a boost. So no, at this point we're about to get like 3 different velocities going on. We got the velocity of the guy in the boat relative to the surrounding water, which is 10 meters per second. Okay? We got the river relative to the outside world, or relative to this tree, which is 5 meters per second. Okay? And you might remember from last semester that you can add and subtract velocities. So what is this guy's, the riverboat speed compared to the tree, right? And paddling towards the tree, it'd be 10 plus 5, 15 meters per second. But then he has to turn around and paddle upstream, which is like 10 minus 5, which is only 5 meters per second. You guys got that? Okay. So let's put this guy. So one way he's going 120 meters at 15 meters per second. Then plus the other, now he comes back 120 meters at only 10 minus 5 is 5 meters per second. Okay. So what's his round trip time? Let's see what is this? 120 divided by 15. Okay, that's 8 seconds plus 120 over 5. Right? Comes out to a total of 32 seconds. And now you can see who wins the race. The guy in the lake wins the race. So if you raise your hand for the lake guy, then yeah, you were right, right? Because that's a smaller time, so he's going to win the race, right? You guys got that? Right. Now, there are different variations on this question. You could have 2 people racing side by side who one guy paces himself and the other guy sprints and then gets winded and comes back slower, right? And in general, the guy who paces himself is going to win. In this case, the guy in the lake with the stagnant water is going to win. Okay, right, you guys said. Right. Now, hold on to this idea because this is going to come back later. Let me do one more classical classical physics relativity example with you guys, okay? Because that is relativity. That's just classic Newtonian relativity. We're not at Einstein yet, right? Einstein relativity coming in a few minutes. Do another one. Suppose you can throw a baseball at like 50 let's say 50 miles per hour, 50 miles an hour, right? And then you get into right. Get to the back of a truck. Okay. And the truck itself is moving at like 20 miles an hour. Right. And then you're back here and you're going to be throwing this baseball. And then there's this guy over here with a radar. So he says, like, how fast is the baseball being thrown? Right. So if you throw this baseball forward, how fast does this guy register on the radar gun? Is the baseball going? 70, right? 50 plus 20 is 70 miles an hour. Unless you throw the baseball backwards. As if you throw the baseball backwards while the truck is moving forward, now how fast is it going relative to the outside world? 30, right? Because 50 minus 20, right? So how fast is the baseball going? Well, is it relative to the guy throwing it, or is it relative to this guy outside the moving truck? Because those are different answers. I guess too. But again, that's just classical Newtonian relativity. You can just very simply add or subtract the speeds, right? So you guys good so far? Right? All right. You guys ready to kickstart this crazy, wacky relativity adventure? Right? Because there's some ground rules for great. You can add or subtract velocities. Everything's all fine and good. Right? All right. Now let's go to 1849. Right, so 1849. There's this guy, Armand Fizeau, trying to figure out what is the speed of light is the question he's trying to figure out. What is the speed of light? Okay? Now, this question's been tackled before. I think Galileo tried to tackle it, but had like an experiment that didn't really work. Actually, we did come across this a few weeks ago. Do you guys remember a Danish astronomer named Olromer? You guys remember him? Right? He was here. Remind you guys what was going on. He was watching one of Jupiter's big moons, Io, orbit Jupiter. And he noticed that as Earth was kind of headed towards Jupiter versus as it was headed away from Jupiter, that the frequency that Io would orbit Jupiter varied. It would like speed up and slow down. Now, it wasn't really speeding up and slowing down. He was observing a Doppler shift. Now, he recognized that, and he put together some solar system geometry and played off the Doppler effect and said, I think the speed of light must be about 2.2 times 10 to the 8 meters per second, which actually isn't that far off. Our modern day understanding is like 3.0 times 10 to the 8 meters per second. So back in the 1600s, whenever, It wasn't super accurate, but it was the right order of magnitude. Now in 1849, Fizeau, this is a guy who gets like modern day type accuracy. He gets it within about 2%, right? Like modern day understanding 3.0 times 10 to the 8 meters per second. Now, how do you do that? He said, I'm going to have this tooth wheel, this cog wheel, and I'll have a light source and an observer. I have them side by side here, kind of crammed on this page, right? On one side of the wheel, and way off in the distance, like many kilometers away, 5-10 kilometers away, I'll have a mirror. Okay, so I, the observer, I'm looking sort of like through these gaps in the teeth, and I see the reflection of this light source. Okay, now that's before this thing is rotating at all. Right? So imagine it's not rotating yet. Right? So you just got a tooth wheel. I'm looking through the gaps. Right? I see the reflection. So that's all fine and good, right? Now let's give this thing a spin. So that could be omega, angular velocity. You could quantify in radians per second. Okay. Now, what's going on with this light beam? Let's follow this light beam that's in red here. All right. Well, some of the light beams are just going to immediately hit the teeth and never make it past. They don't even reach the reflection. So whatever, they don't have to. But some light beams actually do go through the gap. Right? And if the wheel wasn't rotating, it would just come back through the gap, and the observer sees the reflection. Right. But if the wheel is rotating, in fact, if you get it rotating fast enough, then on the return trip for this light beam, where there used to be a gap is now a tooth. If it moves just a little bit, just this little sliver that I've labeled theta, you guys see that little sliver theta, right? So that on this whole return journey, like some distance d and back, we're talking about like kilometers, so some crazy distance like across town and back. Right? I think you first did this in Paris, is where this experiment was first done, right? Is like this whole wheel would rotate just that little sliver, so that where there used to be a tooth is now a gap, and where there was a gap is now a tooth. And what would that look like from the observer point of view? Like looking at this mirror way out in the distance, is you wouldn't see the reflection at all. There would be no light reflected. Oh, so and what about like leading up to that angular velocity omega? Right? So if you weren't spinning it fast enough, then it'll go a little faster, a little faster, a little faster, and until you reach that omega. Right? What that would look like from this observer point of view is you see like a door closing on the reflection of the light. And when that door exactly eclipses that light, then you know you've hit exactly the equilibrium angular velocity to make this whole thing happen. Okay? And so here's three green boxes that got set up. I know that the distance the light travels there and back is speed times time. So it's got to go all the way to the mirror and back. Okay? I'm ignoring this distance, might be like a few centimeters, but this distance is like several kilometers, right there and back. Okay? So that's 2d, where d is the distance of separation. C is the speed of light, and t is how much time it takes to, again, go there and back. Okay, so you guys got that? Okay. Right. Meanwhile, this wheel is rotating. I want it to rotate just this little sliver, just a few degrees theta, except maybe I'll measure in radians, right? Because that's more mathematically pure way to do that. So, 2 pi. Hey, guys, could that be like 2 pi radians? Like 1 revolution? That's what that is. There's 1 revolution. So 2 pi radians divided by 2 times the number of teeth. Now, why 2 times the number of teeth? Suppose there are like 100 teeth. And that means if there are 100 teeth, for example, then this whole wheel has to rotate 1 out of 200 so that the tooth can replace the gap next to it. You don't want the tooth to go all the way to the next tooth. Yeah, you just want the tooth to go to the next gap. So that's why there's a factor 2 on the number of teeth. Right? You guys see that too? Right. You might see that the 2's going to cancel, but I left them there just so you can see where all the bits are coming from. Right. Also, you got a distance equals speed times time in an angular sense, a rotational sense. So here's radians per second, here's time, right? Okay. And this theta and this theta, that's the same theta. And this time and this time, that's the same time, right? Here's the time for light bounce back and forth. Here's the time for the wheel to rotate, just that little sliver, right? So you put it all together, do a bunch of algebra, takes a good amount of paper. You can get, this right here. Here's the speed of light, just in terms of variables. I'll have you guys do this later this week too. As one of my plans, I got this printed up. See if you guys can solve some scratch with different size wheels and different distances and different blah, 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 right? Can you calculate what is the speed of light, right? So here's what he got. And he got 3 times 10 to the 8 meters per second. Okay, so that's all fine and good so far, right? And then people started thinking, hey, what about if you take this and orient it at maybe like different directions, right? Like, and they started thinking about the effect that the Earth is rotating, right? So here's the Earth, equator, pole, all that, right? Like if you bounce light east and west versus if you bounce light north and south, right? Well, maybe that's a different type scenario. Like we got the Earth rotating. It's going like 1,000 miles an hour approximately at the equator compared to the pole. And that's not the end of the story either. It's like, well, the Earth is also revolving around the sun, so there's another huge added speed. Now, I don't think they knew back in 1849, but we know nowadays that our solar system is rotating around or revolving around the Milky Way galaxy, so that would have an effect too, right? They were thinking about these relative motions and thinking it's sort of like, that's why I started with these guys in the boats, right? Like if nothing was in motion, then you could just do the experiment and be like just the guy paddling around the lake. It doesn't matter which direction you go in the lake, your speed is the same regardless, right? But if you got this relative motion going on, right, the Earth's spinning and also revolving around the sun and the whole deal, right? Then if you bounce it east and west, well, sometimes you're traveling with the motion, sometimes you're traveling against the motion. That's like the guy in the river, right? Versus if you bounce like north and south, well, it's more like the guy in the lake, right? That has nothing to do with like the motion, right? Like the spin of the Earth and around the sun, the whole thing, right? Right. But it turned out it didn't matter which direction you oriented this experiment, you always got the same speed of light, right? Which didn't exactly match what Newton would have predicted, but okay, that's what the science is showing. Okay, so you guys good so far? Right. So we're gonna fast forward a few decades and hold on to that because that ends up being like critically important down the line. All right. Let's go to 1887. There's these two guys, Michelson and Morley, right? And they're going to set out to determine like what is the relative speed of the Earth compared to this luminiferous ether. Now, if you've never seen this term before in a science book, that's probably a good thing because this is an experiment that they set up to answer some question, right? Accidentally disprove the existence of this ether. Now, their thought process going in is, let's say it's like 1886, right? What was sort of the conventional scientific thought at the time? Is say, well, we see that waves need mediums to, or like some kind of medium to travel on, right? So like sound needs some kind of medium to go through. Like if this room was a vacuum, you wouldn't be able to hear me talking right now. Or if you send like a pulse on a rope, the rope is some kind of a medium, right? Need that to send the pulse, right? Well, light can be shown to be a wave. I know we got like the double slit experiment. Shining a light through two slits creates an interference pattern, therefore light's a wave, they say. Right, so there must be some kind of luminiferous ether, I think, for this light to be traveling on. Right? Now, nowadays we know that light can travel through a vacuum. That's what I told you guys a few weeks ago, right? Light can travel through a vacuum. Right? They didn't know that back in the day. Experiment disproved this ether. Right? So the experiment was set up. So let's have a light source. Right? Let's follow a light ray, and we'll have this this half silvered mirror, a beam splitter at a 45-degree angle. Right? Now, what that means is that if you shine a bunch of photons at it, like half the photons pass through and half the photons going reflect, right? Okay. And then say the ones pass through are going to bounce off this sphere and then reflect back off this half silver mirror into this observer, right? Or what about the photons, like the ray of light that reflected originally, but well, they'll reflect off this sphere and then go through and then reach the same observer there, right? So we got that, right? You guys got that, right? Now, the first time they did this experiment, what they got was that these two light rays were exactly in phase with each other, which means that they traveled at the same speed, right? Which they weren't really expecting, but that's what they got, right? Oh, this distance is this distance. They're the same distances, right? So if it's all the same distance, light travels all at the same speed and got to them all at the same time. So, okay, that's an interesting result, right? But what if we, again, like orient this in a different orientation? Maybe this is like east-west or north-south, right? So again, what they were kind of expecting is like if this was east-west and this was north-south, right? If you bounce something east and west, like whatever passed through originally and bounced back, it has an east-west motion, right? Okay, that's kind of like being the boat in the river, where part way you're with the current, part way you're fighting against the current, right? Versus the north-south line, well, that's more like being the guy in the lake, where the motion of the planet and the motion of the light beam are perpendicular to each other, so they don't affect each other, right? This is what they thought, right? On top of that, they said, well, if you got, again, like the Earth spinning in space and also revolving around the sun, if there was some luminiferous ether, yeah, that's kind of like a boat going through the water too, or maybe there's some kind of relative motion going on, right? But it didn't matter if they did this at day or night, or if they do this experiment like 6 hours later, or if they do this maybe, how about the summer versus the winter, right? When the Earth is on opposite sides of the sun, right? That didn't make a difference either. Like they were hypothesizing that at some point these waves should be out of phase, and therefore they could use that to calculate what was the speed of the luminiferous ether relative to the Earth, right? But over and over and over, they got this result where the waves were always in phase, regardless of when they did this experiment or how they oriented it. right? They're getting the same thing, right? That was, again, like really unexpected, didn't really jive with Newtonian mechanics, and they had unintentionally disproved the luminiferous ether, right? But you're not exactly sure what to do with that, so they put that aside, right? And then along comes Einstein in 1905 and reinterprets those experiments and comes to a really wacky conclusion. Okay. So here, let's look at Einstein's train here. Okay. So here I got a couple of observers. One guy's inside a boxcar, got it on wheels, and one guy's outside the boxcar. Notice they both have their own stopwatches. So they got their clocks, right? Got kind of cartoony version of this, right? Right. Right. And let's say the guy inside the boxcar, he has a light source on the floor, right? Got a little flashlight. Right? He's got a mirror on the ceiling, and he's going to flip the on switch, or I guess a fire, or whatever they had in 1905. And he's going to follow a ray of light, and it's just going to go straight up and down. So it bounces off this mirror, off the ceiling, back to the source. Right? So up and down. That's all it does, just up and down. So that's pretty straightforward, right? Right? Then he breaks out the toothed wheel and does the whole Fizeau experiment and calculates what is the speed of light, what's the speed of light. So that's all good, right? Right. So good so far, right? Right. Now, one of the first things that I ever taught you in this class, let's go back to like August, September timeframe, is suppose you're sitting in the passenger seat of a car and you're blindfolded and your friend's driving the car on I-95. Can you, the passenger, feel how fast the car is going? No, you don't know. You don't know if it's going 55 miles an hour or 60 miles an hour, or if he's putting along at like 30 miles an hour, right? You've got a cop there, you're going too slow. You can't feel that. Okay? You can feel accelerations, but you can't feel speeds, right? So go back to this guy in the boxcar. Right? Yeah, he sees the beam just going up and down, but he doesn't even know if the car's in motion. This guy outside the boxcar knows if the car's in motion, and if it is, how fast. So maybe some V for velocity, like velocity of the boxcar, but only this guy knows what that V is relative to him, right? Right. So this guy would say that beam actually did not go straight up and down. This beam actually traveled along this diagonal path. It actually traveled a further distance than you thought it did inside the boxcar. Inside the boxcar, he said it just went the short distance, just straight up, straight down. That's it. Right? The guy outside says, no. Actually, it traveled along this crazy diagonal path, which is a further distance, right? But if this guy broke out a toothed wheel and measured what is the speed of light, he would also agree on what is the speed of light. Both these guys agree the speed of light is the same, even though they're in different frames of reference, right? Which is weird. Let's go back to this idea of right. You guys remember the guy in the truck throwing the baseball, right? And I said, oh, you could just like add or subtract the velocities relative to this guy with the radar gun, right? Well, what if we trade out the truck with a rocket? Let's go to space, right? And let's have some guy on a stationary planet. So here's a guy on a stationary planet, right? And here's a guy in a rocket. And what if this rocket is traveling at like half the speed of light, 1/2 c? That could be half the speed of light, right? And he throws on his light beams, right? And breaks out a toothed wheel and measures what is the speed of light of these light beams. Guess what this guy inside the rocket traveling at half the speed of light measures as the speed of light of his light beams? The speed of light, c. What about this guy in the stationary planet? Guess what he measures as the speed of light of those light beams? Also the speed of light, c, right? Which looks completely different than throwing a baseball on a truck, right? Baseball on a truck, well, are you on the truck or are you off the truck? These two different people are perceiving two different speeds of the baseball. But these two guys, the guy on the planet and the guy in the rocket, both agree on what the speed of light is, right? Right? You guys see there's like a mismatch there, right? So back to this train then, if both these guys, the guy inside the train, the guy outside the train, say, yeah, the light travels at the same speed, but they see it traveling different distances for that same speed, that means they have to disagree about what other variable? Distance, speed, time. They're perceiving two different passages of time, right? And the connection is just very simply a Pythagorean theorem, right? That's all this is down here. You guys see a very nice looking right triangle, right? So the short leg of the right triangle, that's say like the distance the guy inside the train car sees it go. It's just c times t, speed of light times t, right? And I threw a little subscript not and colored the c red for the guy inside the train, right? The guy outside the train sees this leg of the triangle, vt. Now that's the speed of the train is v, right? And I just left the plain t and colored it green for the guy outside, right? And then the guy outside would also see the light travel along the diagonal path. So I have the same speed of light c, that c and that c are the same c, right? But this t and this t naught are different t's, right? This green t could be that t, those t's are the same, right? So we got that relationship. You guys see that Pythagorean theorem relationship, right? Right. Now the next thing I might wonder is, well, how do those two times compare? How does this guy's passage of time compare to this guy's passage of time? Because they're not the same time, right? So you can do some algebra. I skipped a bunch of algebra steps. Go from here to here. And that's what you get. Here's the guy inside the car. Here's the guy outside the car. And they perceive different passages of time. Okay? So you divide by the square root of 1 minus v squared on c squared, where v is the speed of the train, c is the speed of light. Right? The square root 1 minus v squared on c squared is called the Lorentz factor. Okay? You guys see that? Right. So if you ask Newton, what's the nature of time? He would say, well, the time probably beats the same for everyone everywhere. It's kind of like a built-in assumption. Right? Einstein says that's actually not true. The faster you're going, the slower time beats for you. Let's go through a couple examples. Right? Let's start just at rest. Something called correspondence principle. You guys know what the correspondence principle is? Right? Correspondence principle says if you come up with some crazy new theory about how something works, then it better at least agree with the correct predictions of the old theory, right? So Newtonian mechanics got us all the way to 1905, you know, with a couple of weird exceptions. So they were a couple of right. So this should at least be consistent with the correct predictions of Newtonian theory, right? So let's try that. Let's say that both these guys are at rest. What does this equation say? So that'd be v is equal to 0. Guys, what is 0 squared? 0 divided by c squared is 0. 1 minus 0 is 1. Square root of 1 is 1. So t naught divided by 1 is just t naught. Oh, look at that. T is equal to t naught. Okay, so these two guys can agree on how much time has passed as long as they're both at rest. Right? In fact, as long as you plug in any slow speed, so you could call it non-relativistic speeds, that'll also still be approximately true. Right? Like the fastest I think anyone is moving relative to anyone else is probably anyone in the International Space Station is orbiting the Earth every 90 minutes. That's really fast, right? But even that is not really a relativistic speed. That's so slow compared to the speed of light. Like how about this? What if you even had 10% the speed of light? That seems pretty fast, right? 10% the speed of light seems pretty crazy. Let's try that. 10% the speed of light divided by speed of light. So that'd be 10%. But then you square that, that's like 1%. 10% squared is like 1%. 1 minus 1%, that's like 99%. The square root of that is like 99.5%. Okay, so then, yeah, there's a mismatch in time, but you wouldn't even be able to notice that with your human brain, right? You would need some kind of special equipment to notice the difference, right? Okay. You can take atomic clocks up into the International Space Station, show that, yeah, there's a tiny difference of time for International Space Station compared to Earth, right? It's not very much, but you can show that it is there. Right? In fact, you need Einstein relativity to correctly run GPS, right? Like if Einstein had never come up with relativity and say somehow no one else had, right? You know, by the time we have GPS, GPS wouldn't actually work, or at least all our clocks would be off and you have to like manually adjust them and not really know why, right? So yeah, you need relativity to have GPS, right? Right, you guys good so far? Right. Oh, let me show you guys. Actually, you know what? I've got an animation of this. I think I'm gonna save it for the end of class. Right. I've got an animation of this too. Right. So I'll save that for the end of class. Right. Next thing I want to say is that if time dilates, then that can't be the end of the story. There has to be more to this space time. I'll give you guys a story example why. Right. Let's say we're here on Earth. Let's say E for Earth. Right. And we're going to blast a rocket over to, let's say, way off in the distance is like some distant solar system, like way off another part of the galaxy, right? Let's say this distance is like 10 light years. So I'll say distance equals 10 light years, right? What does that mean? That means if you like send a radio signal, it would take 10 years to reach there, or whatever light's coming from that distant solar system takes 10 years to reach us. We're seeing 10 years into the past, we're looking at, right? And let's say we speed up this rocket really close to the speed of light pretty quickly. It's like 99% of the speed of light, and then just goes and then slows down really quickly, right? Well, the minimum time it would take to reach that solar system would be 10 years, right? If you could travel like 99% the speed of light, right? Is that true? Right. Now, combine that though with what I just told you about these two observers, right? I'm going to refer to this green hat guy as Earth twin, and this red hat guy is like rocket twin. Replace this boxcar with a rocket. That's basically what we're talking about, right? So from Earth Twin's point of view, he says, yeah, that process took at least 10 years. But from rocket twins' point of view, suppose you put on like 99% the speed of light here, right? Let's try that out. This fraction is really close to 1, but a little bit less. 1 minus something a little bit less than 1 is maybe it's like 0.01. Take the square root of that, right? You're divided by a tiny number. If you divide by a tiny number, then Earth twin's time is going to be a lot bigger than this rocket twin's time. So rocket twin, if he's traveling at 99% speed of light, he might think this whole journey takes like a year. Instead of Earth twin says, no, it took you like 10 years to get there at least. But if you're on the rocket for the ride, you might say, no, it only took like a year, right? But if the speed of light is like limiting speed limit, like no one can even get up to the speed of light, right? Then the only way for that to be consistent, to go 10 light years in 1 year, is for this distance to have shrunk. In fact, that's exactly what rocket twin would have perceived, and that's this next poster right here, right? So it's not just that time dilates, right? Here's rocket twin, here's Earth twin time, so they got a mismatch in time. But there's also a length contraction, right? So if you travel near the speed of light, now this Lorentz factor is between 0 and 1. This Lorentz factor is always bounded between 0 and 1, right? That original 10 light years now might only shrink down to like 1 light year of distance. Ooh, right? Again, only if you're along for the ride in the rocket. And also Earth twin, looking through his telescope at that rocket as it's in motion, is going to view a shortened rocket. Now, if you're on the rocket, you could break out a meter stick and it's like, oh, it's the same length it always was, right? But if Earth twin's looking through a telescope, says, well, your rocket used to be like 10 meters long and now it's only like 1 meter long. So what happened, right? The third dilation that happens is a momentum dilation. Sometimes you see it as like mass dilation, momentum dilation, right? Now this one, it looks a lot like the time dilation formula, right? Particle physicists over at Large Hadron Collider and CERN see this all the time. So over in Switzerland, there's this huge particle collider. It's like a giant ring. Right? It'll take like little particles, like little protons or hydrogen atoms, right? And wheel them around like 99-point-something% the speed of light. Right? And to keep it in a circular pattern, they've got this magnetic field all the way around. I'm going to represent that with like a horseshoe magnet, just kind of cartoony version. Right? And I remember centripetal force, which in this case provided by that magnetic field. So centripetal force is something like mv squared over r. So see if you know what is the mass of the proton you're putting through this circular path, right? How fast is it going? What's this radius of curvature, right? The more massive it is, the more force you need. So it's okay, I'm putting in 1 gram of protons, okay, and let's speed around, right? And then you speed up near the speed of light. What you'll notice is that it's as if there's even more mass that manifested, right? There's like more momentum. So you have to increase the strength of this magnetic field to keep everything on a circular path, right? So particle physicists see this momentum dilation all the time. Right? I made a graph for momentum as a function of speed, which looks the exact same shape as time versus speed. So I could put time up here, it'd be the same looking graph, right? There's not. I should have made one for L2 that would like go down 0. But anyway, let's focus on this one. So we're particle physicists. We're speeding up particles, right? Now, what Newton said was in this green box. He said momentum is mass times velocity. You guys remember that one from last semester, like collision physics, collision carts? Momentum is mass times velocity, right? So, right, Einstein's equation is this red curve, though, right? And here's the red equation that goes along with this, right? It starts out as agreeing with Newton, or at least pretty close to. So as long as you're non-relativistic speed, it's like, okay, you can use Newton or Einstein. They're both pretty close to each other anyway, right? But as you get closer and closer to the speed of light, right, now they're going to deviate wildly. And notice you can never quite reach the speed of light, because if you plug in the speed of light here, you're actually dividing by 0. Hence this vertical asymptote, right? Right, you see that too? Right. Now some interesting consequences too. Let's think about, what if I replace this axis with time? It'd basically be the same graph, right? Time, what would that mean? What does it look like to travel at the speed of light? Now, nothing with mass can travel the speed of light, but light does. Actually, anything that's massless always travels at the speed of light through space. Okay, so that was the question that Einstein had when he was formulating all this to begin with. So, what would it look like to travel along with a light beam? Okay? And if you put time on this axis and get again like the same type graph, there's a really weird consequence to that, which is that time becomes infinite. Or a way you can think of that is like all time is happening at once. So from the point of view of photons, there's kind of no such thing as time. It's like all time is passing all at the same time. Right? There's a similar effect, by the way, when we get to black holes. You guys saw black holes last week, global astronomy, right? If you go to the black hole, the gravitational field will also warp time. So if you were to look at the rest of the universe as you're falling into a black hole, you would see all of time in the universe just pass all in a blink, right? See all the stars fizzle out, all that, right? And for length, let me go back to my equations for length. I should have a graph for this too, but got the equations anyway, right? What happens to length, right? From a photon's point of view? Well, if you travel at the speed of light, that's c squared over c squared, that's 1. 1 minus 1 is 0, square root of that is still 0. Any length times 0 is 0. So space also does not exist from the point of view of photons. So if you're traveling along with photons, you don't really experience time or space, right? Which is interesting. We do experience time and space, and we see photons like zip around all over the place, right? So interesting difference in perspective, right? Okay. All right. Minkowski space-time diagram. There's a 2D version of this. I gave you guys a fancy 3D version, but I got 2 spatial dimensions, x and y. You guys know we live in a 3 spatial dimensions universe, so I kind of stripped that down to 2. Again, sometimes just strip down to 1 is fine also, right? And then on the vertical axis, think of this being like a time axis. Now, a lot of diagrams do speed of light times time just to get all the dimensions constant, meters, whatever, right? But basically think of this like time, like a time axis is vertical, right? So what's the story you can attach to this? Well, if you're just sitting at your desk, like at rest, okay, you're not moving through space, but you are moving through time, right? So time's ticking. So it's kind of like moving up this diagram. It's up. So you just like move it up if you're at rest. If you get up and start moving around, well, now you are changing your location with respect to time. So now you aren't moving exactly up this axis, right? But you're moving maybe off course. In fact, the faster you're going, you're approaching this dashed line. And if you get up close to the speed of light, which you can never quite reach, right? Then you're really close to this dash line. That's why I made it dash, because it's like an asymptote, right? You can never quite reach the speed of light. Right? So you guys see how that? Right. And this 45-degree angle has to do with like c times t. So there you go. Right. And these 2 green cones is all that can have any kind of cause or effect relationship with you, like at this origin point here. Okay? So if there's some event that happened that's like outside this cone in the past, like for example, if you look at, like, there's the edge of the observable universe in that photo right there, right? But anything that's going on there, like in that picture, can't really affect us. There are definitely any galaxies that are beyond that. Right? They're just too far away, right? It doesn't matter if some alien like fired a space gun right at Earth, like, we're gonna get them, right? It's never gonna reach us like at this particular time, right? Maybe in the future, but not at this moment. And same thing going into the future. Like, what can you affect going into the future? Well, only anything inside this green cone. Like anything that happens like over here, like what happens on Mars 5 seconds from now. It's absolutely impossible for anyone to affect what happens on Mars 5 seconds from now, right? Because it's just too far away. Nothing can reach Mars in 5 seconds. Right. All right. Then, you can take these relativity equations, that mass dilation. You can rearrange it to get mass energy equivalence. So this is Einstein says is mass and energy are like 2 sides of the same coin, right? Which is weird because they're like different units also, right? It skipped a bunch of the proof and just narrowed it down to these like last couple of steps. So this is the energy of nuclear reactions, right? Now here's mass, here's energy, here's the speed of light, that's being squared, right? Do you guys remember back in chemistry, you guys learned conservation of mass? So you could have any kind of crazy chemical reaction, which this is not referring to, but chemical reaction, mass was conserved. So you added the mass of all your reactants, mass of all your products. It's like, oh, it's the same mass. It's like 32.14 grams before and after, right? Okay. But nuclear reactions, well, there's a huge asterisk on that. With nuclear reactions, you're going to be missing mass, and that missing mass is all converted into energy. So it doesn't exactly disappear, it just converts into a different form, which is like an energy form. Okay, can you see that? Right, so we talk about nuclear reactions. Let's look at, here's 2 basic categories, well, the 2 main categories of nuclear reactions. You got fission and fusion. Okay. And on this graph, we're looking at binding energy per nucleon, and then as a function of mass number, right? Like uranium, I know it has atomic number 92, I think it is, right? And if you add all the neutrons to it, you've got a much larger mass number, right? Hydrogen is like element number 1, right? There's also an upside down version of this graph. This is like mass per nucleon, right? Nucleon can be a proton or a neutron, right? Like how massive is a nucleon? How massive is a proton? Well, it actually depends what atom it's in. It's really heavy inside of hydrogen. It's not nearly as heavy inside of helium, and so on. Right? It's lightest inside an iron. That's what Fe is, right? Iron. Okay? So if you turn that back around to the graph I have right here, binding energy per nucleon, right? Like how much energy goes into like binding these nucleons together, right? Well, if you take a big atom like uranium, right, you can say fire a neutron at it and split it into say like krypton and barium. This is like the main nuclear reaction that happened, and it released a ton of energy. That energy on this graph you can sort of think like a height change as it splits from uranium to some of these smaller elements like barium and krypton and some of these other. There's a height change. That height change is going to manifest into energy. E equals mc squared. Right. Now you can go the other way. If you start with hydrogen and you fuse 2 hydrogen atoms to make helium, right? That is a change of like almost 1,000 times as much as a fission reaction, right? So the first reactions we got were these fission reactions, right? Actually, all our nuclear power plants right now are all fission, right? With fusion going from hydrogen to helium, we know how to make a bomb with that, but we haven't actually been able to turn that into a commercial power plant yet, right? Hopefully soon. Otherwise, we're all going to die by the end of the century. But yeah, that could be a fusion reactor. Hopefully, it comes online pretty close, right? Right, and then right. I might take this one for another day because general relativity. General relativity, we're going to incorporate gravity, and that can warp space-time too. But I wanted to show you guys that animation of the twin paradox before you guys take off today.